Also, our speaker was negative, so we can start with the second lecture. Yann.
Well, so I caught it 2.5 months ago, and I had 4 shots before that, so I think I'm pretty immune for a while at least. Right, so back to energy-based models. So just a reminder, we use an implicit function that we want to give low energy to on the data points and higher energy outside, and it tells us the degree of incompatibility between 2 sets of variables, or perhaps the degree, in the sort of unconditional version, the degree of internal coherence of y. So the example I used yesterday is that if we had an energy function that could tell us if we had a high quality photo as opposed to a bad quality one, we could use this to do image restoration or super resolution and things like this. And we stopped at this slide that said you can transform energy-based models into conditional probability distributions if you want, or joint distribution, if you can compute this integral. And generally, you can't, at least for interesting models when y is more than a set of a discrete set with a relatively small cardinality. There's no way you can compute this integral, maybe unless f is some quadratic function or something like that, in which case it's a Gaussian integral. So I'm just going to flash this. I'll come back to this concept afterwards, which is energy-based models with latent variables. So you can define energy functions that depend on a variable that is never given to you, is never observed, but the actual energy between the variables you may or may not observed is simply the minimum over z of the elementary energy function E of xyz. And you can think of this as a 0 temperature limit over free energy if you really want to connect this with thermodynamics, and we'll come back to that. But it's a slightly more general view of energy-based model where the energy itself is the result of a minimization with respect to some variable. And again, I haven't said a word about learning yet. Okay, this is all about inference. So you have the model, and you're trying to figure out how to do inference with it, how to use it, but we're not talking about learning. An example of latent variable model. So this is my way of representing probabilistic or non-deterministic, I should say, not probabilistic, but non-deterministic functions. So a non-deterministic function can always be seen as a set of deterministic functions where one of the input is a latent variable whose value is not determined by any of the outputs directly. Okay, so I can parameterize any distribution by essentially having a latent variable that is being drawn from a particular distribution and is being passed through a function. Could be a neural net, or could be something very simple or very complicated, doesn't matter. And that will imply a distribution over the prediction, right? So as I swipe z over the input distribution, or I sample samples from z from that distribution, I will get a distribution over the output, right? But the advantage of doing this is that all the functions I'm going to write down are all deterministic functions. So whatever thing is not deterministic is going to be pushed into a latent variable, which may or may not be probabilistic, in the sense that, for example, my latent variable may not be sampled from a distribution. It could be just chosen within a set. Okay, in this case, some sort of rectangle. And then when I make this latent variable swipe over that set, then I'm going to produce a set of outputs, a manifold on the output that depends on the function that's inside of this. Okay, and that's a way of basically parameterizing multimodal predictions. So this allows the model to make multiple predictions, not just one. If the latent variable is drawn from a distribution, then it's a probabilistic model. If it's just chosen in a set, it's not a probabilistic model, but it's still a non-deterministic model, okay? Because it produces a set, not a single value, not a point. Okay, now let's talk about how we train energy-based models. And there's basically 2 classes of methods: contrastive methods, which I'll spend some time on, and regularized or architectural methods. So there are certain, depending on the architecture of the energy-based model that you build, you may have to use different techniques to train it. But it's basically those two classes that I talked about, contrastive and regularized. So, or architectural. So here's a very simple example. You take an input, scalar input x, feed it to some neural net with two layers, very simple. And then feed a output y, which is also a scalar continuous value. Compute the distance between the output of that neural net and that variable, and that's your energy function. Okay, very simple. In this case, it's an L1 distance, just sum of it's just the sum of absolute value. Actually, just the absolute value of the difference, because the output here is a scalar. And then imagine we want to train this. Okay, so this looks very much like a regression model, and it is. If we want to train this model, we can just find a set of weights of this neural net that minimize the average energy over a training set, and this will work. It will. We have those data points, the blue spheres. We're going to push down on those blue spheres, and basically, using gradient descent, figure out how do I adjust the weights of that neural net so that a particular blue sphere I'm looking at right now goes down in energy. So basically minimizing the energy, right? And as I push down and the parameters are being changed, the energy surface takes the right shape. So this is the initial shape, and then eventually the groove with minimum energy kind of follows the manifold of data. Okay, so this is a very simple example where this architecture will be perfectly happy if we use a loss function that is simply the average energy of the training samples. But here is another one. So this one, I send both the input and the output to neural nets. They produce a 6-dimensional output, and then I compute the distance between those two, and that's my energy function. And I'm going to do the same thing. I'm going to take every training sample and push down on the energy of each training sample. And what do I get? I get a completely flat energy surface. It all goes to zero. It's called a collapse. And the reason it collapses is because those two neural nets are perfectly happy to completely ignore the input and produce two constant 6-dimensional vectors that are equal, so the energy is just zero all the time. This is not a good model, all right? It's not a good model because it doesn't tell me the difference between what's good and what's bad in the XY space. It just tells me everything is zero energy, not a good model. So I need to find a way to make sure that the energy of the data points is low, but also that the energy of everything else outside the manifold of data is higher. And that's where things become complicated, slightly more complicated. Okay, so we have this collapse. And there are basically two classes of methods to prevent this. One is contrastive methods. So what does a contrastive method consist in? They consist in generating contrastive samples, those green points, in some way, okay, which I'm not specifying right now, and basically pushing up on their energy. Okay, so I'm going to push down on the blue dots, and I'm going to push up on those green dots, and somehow I'm going to have to come up with some way of generating those green dots, right? And so that's going to make the energy surface take the right shape, and then therefore it will capture the dependency between x and y. Here's another idea, okay, and this one is slightly more difficult to understand. It's that I'm going to add a term in the energy or have a regularizer of some kind that basically limits the volume of space that can take low energy. So that whenever I push down on blue spheres, other areas of the space will have to go up in energy because the volume that I let the system use for low energy region is limited, is minimized through some regularizer. Well, so a particular way of doing this is to insist that the exponential minus the energy have a constant integral. So a probabilistic model will do this as long as you can normalize it. Yeah.
So for the contrastive method, you would like to have green point not too far from the data as well. So do you distort images? Or
Yeah.
In which way do you distort?
Good question. Okay, we'll come back to that.
The collapse happens because you pass both the input and the output in a network, and so you make the loss degenerative. as you say, they could all go to zero. But why would you want to do that? Why can't we stick to keeping the output as it is and just manipulating the input?
You mean why don't we use a model like this one?
Right. Why do we need to use?
So this one does not have any capability of multimodality or non-deterministic outputs, right? You put an input, you get one output, and that's it. So for a given x, you can have only one y that has low energy for this thing, right? And the y that has low energy is whatever is produced by your neural net. So if you do regression, that's fine. If you want to do prediction where the prediction has multiple possibilities, like, right now I can go left or right, I can move my hand in one particular way, and all of those are plausible future for where I'm starting from, then those models don't work. They can't handle multimodality. So if you want to handle multimodality, you either have to have a model of this type, which later I'll call a joint embedding architecture, or one of those latent variable models where the latent variable can vary over a set and then produce multiple predictions.
In the joint embedding, is the idea that multiple candidate y's match x should match to the same embedding?
Yeah, so you can have, so the essential characteristic of this one, and I'll come back to this at length, is the fact that this neural net can have, or trainable function, whatever it is, can have invariance properties. So there can be entire sets where you vary y and the output doesn't change. And what that means is that all of those y's will have the same energy for a given x. Okay? So it makes that model multimodal because of the invariance properties of that network. And the alternative is the latent variable model I was talking about earlier. Okay, so let's look at a bunch of standard architectures that some of you may have seen before and see to what extent they can or cannot collapse. So a regression, which is basically one neural net or two, you can think of it as two neural nets, but you can fold this into this if you want. And then you just measure the divergence of some kind between the output and the predicted output. That cannot collapse. We just saw that. It's a regression model or a classification problem. That cannot collapse. Because the system can only produce one output. So this one has a latent variable. So as I vary the latent variable over a set, my output can vary over a set. And if I use an inference procedure by which when I show an x and a y, I find a z that minimizes the energy, and that's my energy, okay? My energy f, then this can collapse. And the reason it can collapse is that let's imagine that z has the same dimension as y, and that the predictor is sufficiently non-stupid to be able to learn the identity function, or some invertible function, okay? Then for any y that I show the system, there is going to be a z that produces this exact y, okay? So the system can happily ignore x, and whatever I give it a y, and I find a z that minimizes the energy, which is this divergence, are going to get zero error. So that's a completely collapsed model. How do I prevent this from happening? And again, I'll come back to this later. I have to limit the information capacity of that latent variable. If I make this latent variable have limited information content, for example, I make it discrete with a small number of alternatives, or I make it low dimensional, or I make it sparse, or I make it noisy, then the information content of that latent variable is small, and then I'll prevent collapse by doing this. Okay, so that's an example of a regularized model, where you put a regularizer on that latent variable to limit its information content, and as a consequence, you prevent collapse. Okay? You kind of have to get used to this idea. So let me take an example. Let's assume you make z discrete with k values, k different values. There can only be k different values for y tilde. Okay, for each value of z for a given x, for each of the k values of z, I'm going to get a different value for y tilde. Perhaps some of them will be equal, but let's say it's not degenerate. So I get k different values for y tilde. And what that means is that in the space of y, I can only have k values that have zero error, that have zero energy. Everything else will have to have higher energy because I only have k points that I can give zero energy to. If this is a square distance, then those k points will be quadratic wells, and as I move away from each of those, as I move y away from any of those k points, the energy has to go quadratically in accordance to this quadratic error. Another example, an autoencoder. An autoencoder can collapse. So an autoencoder, you only have a y variable, you don't have an x. And you run y through an encoder and then a decoder and you reconstruct. Obviously, you can learn the identity function. Okay, if sy is not kind of too low dimensional, this system can learn the identity function and therefore give you a zero energy for every y you feed it. This is not a good autoencoder. A good autoencoder is one that reconstructs the stuff you train it on and does not reconstruct the stuff you don't train it on. Okay, and that's the second part. The second part is this idea that things that is not in your training set should have higher energy than stuff that in your training set. How do you fix this for autoencoder? Again, you have to limit the information content of that representation, information capacity of that representation. The same way here, we did it for the latent variable. Here, we have to do it for this internal representation at some level. Okay, the partition of this system into encoder and decoder is immaterial. You can pick it wherever you want.
So in principle, I guess you can also try to fix an autoencoder by using a contrastive method.
Yes,
you can do it?
Absolutely. Yeah, I'm going to argue against that, but you could. Yes. Okay, and here is the joint embedding architecture. So here, this can definitely collapse in the mode that I was explaining before, where the encoders basically just ignore the inputs and just produce two equal representations all the time, and you get zero error, zero energy everywhere, right? And so that is due to the invariance properties of this encoder. The advantage of this kind of model is that it's multimodal. For a given x, you can have multiple y's that have low energy, but you have to prevent collapse in some way. So every model that can be multimodal can be subject to collapse, and we have to prevent that from happening. And the only ways I know are those two categories. If anyone has any other idea of how to do this, I'd like to learn about it, but I can only think of those two classes of methods. Everything I can think of falls into one or the other. Everything that's ever been published that I know about falls into one or the other category. So again, contrastive methods, put some green points, push their energy up in some way, or have some regularizer or some method that limits the volume of stuff that can take low energy. Okay? So let me take two specific examples. So one, here is an example of a loss function that you can use for a contrastive method. So it's one that basically has two samples, a sample from the data. Okay, so xy is a training sample. So this y comes from the data. It's one of those blue points, right? And then this y hat is, it's hat because I'm going to push up on it, is one of those contrastive samples, which I have to come up with in some way that I've not specified. And then I'm going to use a loss function here that is going to be used for training. Okay, so this is going to be minimized with respect to the parameters of the energy model. And it's going to be the difference between the energy of the good guy and the energy of the bad guy. And I'm going to put some margin that makes sure that the energy of the bad guy is larger than the energy of the good guy by at least this margin. And this margin may depend on the 2 points, so that when the 2 points are really close to each other, the margin is small, and when they're far away from each other, it's bigger. So I kind of, can force some sort of growth between them. And then I put all of this into a positive part, so that whenever this is smaller than this by at least that, then the loss is 0. And then when this is not big enough to be larger than this by at least that, then it's non-zero and it goes linearly in the energy. Okay, it's called a hinge loss. Very simple. This is the stuff that Nati was talking about yesterday. Just one example. I'll come later with a long list of different loss functions you can use. Some of them have been around since the 1980s, actually. And then regularized methods. So I mentioned this idea that you might need to regularize a latent variable in a latent variable model, if you want, so this is not for joint embedding, this is for latent variable model, where you need to minimize the information content of Z. And a good example of this is sparse coding. So in sparse coding, and I'll come back to that, you have a vector here. The regularizer here is the L1 norm of that vector. And then the decoder is simply a matrix. You multiply Z by a matrix, and then you have a squared reconstruction error, and that's your energy function. So the energy function now is the sum of two terms, the square reconstruction error and the regularization term here for Z. I give you a Y, you find a Z that minimizes the energy, so reconstructs but also is sparse. And the entire space cannot have low energy because you force this variable to be sparse. Okay? This is not really interpretable in terms of probabilistic models, but in terms of energy-based model, it's just fine. Okay? It's not a probabilistic model, it's completely deterministic. The way you compute Z from a given Y is just an optimization.
So if you were to sort of try to push up by, say, like, minimizing the height of the blue points, but maximizing the norm of a Hessian or something at the blue points?
Yeah.
Like, would this be contrastive or regularized?
So that's called score matching. It was published by Apo Hivarinen in the 90s, I think. So basically his idea was you push down on the blue points and then you indeed maximize the local curvature, the trace of the Hessian or something like this, of the energy function with respect to the input, right? There's not with respect to the weights. Locally. So it's kind of it's a local regularized method. But it's completely hairy, like you can't use it for anything else than linear models, basically. Even with the automatic differentiation, it's completely hairy because you have to compute the gradient with respect to the parameters of the trace of the Hessian of the energy function with respect to the inputs, and you get, some crazy stuff, right? Also, you need to regularize it, actually.
Maybe just like in the last example with the sparse,
Yeah.
You're always free to think of exponential of R as some kind of a prior. I mean, unless you like
Sure.
push too strongly into it. I mean, it may be useful
You can.
for some part of your reasoning.
You can, yeah. So one way to limit the information content of Z is you make it stochastic, right? So instead of Z being a single point, you make it a distribution. And then the information you can extract from that distribution is limited because the distribution is, not completely deterministic, right? I'll come back to those methods, actually, when I talk about latent variable models. Okay, so contrastive methods versus regularized methods. So I made a list here of a number of different methods and classified as to whether I think they are contrastive or regularized. So essentially, if you're going to do maximum likelihood estimation with some sort of Monte Carlo, Markosian Monte Carlo, Hamiltonian Monte Carlo sampling for the contrastive samples for your log partition function term. It's a contrastive method where the way to generate the green points is to do sampling according to your model. Contrastive divergence is basically a poor man's version of this, so that's same thing. You generate green points that you push up. Metric learning, Siamese networks, so those are for joint embedding architectures. And the classical methods for this is that you have pairs of X and Y that you know are compatible, and then you somehow in your training set pick pairs of X and Y that you know are incompatible. So for example, X and Y could be two different views of this object, or X could be an augmentation of Y, a sort of distorted version of Y if you want. And then you can pick X and Y's that are from two different categories or two different samples. So those are contrastive methods. But you can train Siamese nets with non-contrastive methods. I'll come back to this. I think this is the coolest stuff that has appeared in the last 2 years. Things like ratio matching, noise contrastive estimation, or info NCE, minimum probability flow, GANs. GANs are an example of contrastive method. I'll come back to this. And then masked autoencoders, denoising autoencoders, those are also contrastive methods, particular type of contrastive methods. And then here are things that are regularized or architectural methods. So PCA is an architectural method. You force the representation to have lower dimension than the input, and therefore the The system cannot give low energy to everything. It cannot reconstruct everything. It can only reconstruct what's on the principal subspace, and then everything else will have a high reconstruction error. And so you're limiting the volume of low energy space by limiting the dimension of the representation. K means you're making the representation discrete. I'll come back to this. I'll explain why this works. Gas and mixture model, this is actually architectural because it's, the normalization is hardwired. Square ICA, kind of similar things. Normalizing flow. So those are kind of normalized models. And then you have regularized models. So things like sparse coding or sparse modeling, sparse autoencoders, LISTA, which is a form of sparse autoencoder, variational autoencoders are regularized methods, discrete autoencoders, VQVAE and things of that type. And then other type of methods that I'm not going to talk about. And here you see the score matching idea that you were proposing. I don't know if you'd heard of score matching before, but that's a good idea. Okay, it's complicated to
So is the
use.
issue with score matching only computational, or is it also, because it seems like the score matching doesn't distinguish between a completely random point and something that is kind of still in the image distribution but not on your manifold. Unlike, say, contrastive methods where you have like some intelligent augmentation, here it's in, so is it like only computational score matching?
I don't know, it could be intelligent or very stupid, right? I mean, the masked autoencoder is kind of a stupid way of generating green points by, you show a text and you remove some of the words, you blank them out. Is that intelligent? I don't know. So, I mean, score matching, the problem with score matching is that it's very local. So the behavior of the energy function far away from the data manifold is completely undetermined, unless your architecture is, sufficiently constrained and regularized so that, things behave properly. But you basically get a local good shape for the energy model, which, you really can't predict how it's going to behave far away.
It's just, I mean, if the manifold of your data is kind of disconnected, it's even worse, right?
Yeah.
Because then you have a good local approximation, but you don't know what is the relative height of the energy.
That's right. And if you don't have a latent variable model, and you have two manifolds, what happens right in the middle of it? I'll show some examples of that, actually. Okay, so let's talk about contrastive methods for a bit. So the general form of a loss function. Okay, so this is the loss function that we're going to minimize for training. And you have to really, really kind of keep this in mind. There is the energy function that you minimize with respect to latent variables or with respect to outputs for inference. Okay, no learning there. That's the energy. And then there is the loss function or the loss functional. The loss functional takes the energy function as an argument and it basically shapes it in the right way so that the energy function takes low value on the data points and higher value outside. Okay? And contrastive methods basically say, here's a collection of training samples that I have. Here is the parameter of my energy function. I'm going to take the energies produced by my model for each, and this should be indexed by W somehow, for each of the training samples, and kind of plug them into this loss function in such a way that I push up and pull down, push down and pull up on the right things. So that could be kind of a general form. So here is a specific form where you only have two terms in the loss function: the energy of a data point and the energy of a contrastive point, and maybe some margin parameter that you can compute. So that's a relatively general form for a loss function, but it only takes two samples. And you can do things like, and so ideas like this go back a long time. You can do things like, minimize the energy of the first term, of the energy of the good point, and then somehow maximize the energy of the bad point up to some margin. Okay, separately. So this pins down the energy. So for this to work, you need the energy to have a lower bound. So it needs to be some distance of some kind. Okay, because you don't want this to go to minus infinity, right? So you sort of limit it, and then you push up the energy of bad guys up in proportion to how far they are from the good guy. This is another loss function which is the one that Nati was referring to yesterday, which I already mentioned. So this only cares about the difference between energies, not absolute values. And there is a margin term here, and you plug this into a positive part so that this will push this down below that, or push this up above this by at least that. Okay, and then if that condition is satisfied, the loss is 0 for this sample. And then, other types of loss, you can square them, which, maybe will allow the system to find a better balance between the positive and negative, things like that. So, yeah, this is just a kind of a graphic representation of this hinge loss. Sometimes people call this a triplet loss too, because you have 3 samples, basically x, y, and y hat. And you're trying to say, I want, let's imagine this is some sort of distance, okay? What you're telling the system, I want the positive y to be closer to me than the negative y by at least this margin. But in reality, it's rarely a distance. Most of the time, it's a distance between y and some function computed from x using a neural net or something like that. Or it could be a joint embedding, whatever. In fact, here's a whole bunch of loss functions, and some of those go back to the 1980s. So, because they were used by people who were doing discriminative methods applied to speech recognition. So they were basically getting scores for different interpretations of a sentence. And then, what do you do with those scores? Well, I need to give a good score to the correct interpretation and bad scores to the bad ones. And I have a latent variable, which is, which path in some graph that I search of possible alternative interpretation that I minimize upon. But here the latent variable does not appear. We assume that we work with f, and whatever latent variable we had was removed through minimization or something like that. So energy loss. Your loss is your energy function over your training sample. It might work depending on how you design your architecture, but basically there's no guarantee it will not collapse. Okay. This is the perceptron loss, or generalized form of the perceptron loss. So this is the energy of the data point minus the lowest energy that your model can produce for this given x for any y. Okay, so in the perceptron case, y is a binary variable, +1, -1. And this is whatever answer, this is the energy that your model produces for whatever answer it wants to produce. And this is the energy of the correct answer. So when the system produces the correct answer, the difference is 0. And when it produces the wrong answer, the difference is positive. Okay. It's not a good loss function for unconstrained f because the margin is 0. Okay, there's no guarantee that this thing will not collapse. But if f is linearly parameterized in w in the parameters, then it works. Okay, it doesn't collapse. I'm not going to go into the details of why, because it's not particularly interesting, but it's kind of an interesting characteristic of the perceptron loss. Hinge loss I already talked about. It's just a rewriting of the same thing that I wrote before. There is a margin that you just put in, you choose. Log loss, so this is what you use for logistic regression. It's the log of 1 plus the exponential of the difference of the energies between the good guy and the bad guy, right? So this is going to push this entire term to be large and negative. Am I missing a minus here? I think. Okay, now you're minimizing this, so you're making this energy small and this energy large. And you can think of this as some sort of soft version of this. So this is a hinge with a corner, and this is sort of a soft hinge, if you want. Okay. But it's basically behaves more or less the same way. So this is obviously will push down on the energy of this guy and push up on the energy of that guy. Here the margin is infinite. Like the system would be happy if that energy was infinitely large and this one infinitely small, or was taking its minimum value, whatever it is. LVQ2, so this goes back to the 1980s, work by Teuvo Kohonen. But I'm not going to go very precisely into this. This is it's called I can't remember what MCE stands for actually, but it's basically an approximation of classification error. So this is a logistic function, a sigmoid. And this wants to make, again, this energy really small and this energy really large with some sort of logistic function type cause, so that if the difference between those two energies is small, then they're almost the same. You get a high gradient. If this guy is really small, this guy really large, it's flat. And then if this guy is really large and this guy really small, it's also flat, which may or may not be good, okay? But it's a soft approximation of the number of classification error. I think that's what it's called, minimum classification error.
So the word you have never pronounced, which is convexity of the loss function with respect to f,
yeah.
is important?
Yes. Well, yes. So this one sucks because it's non-convex.
No, but
yeah.
my intuition is that you have to be convex at the loss level, otherwise it's complicated.
You don't have to, but it's better. I agree.
Okay, so you agree with your own state, but
Yeah, yeah. And this one was used briefly in speech recognition, but it's non-convex. The other ones are. Doesn't mean they're good, but this is convex. This is convex. So this one you attract quadratically the energy towards 0 for the good guy, and then you repel the bad guy with an exponential. And this is what you have to use if you are a probabilist. So if you are really interested in the fact that f should be some sort of log of probability, then you have to do maximum likelihood or minimum negative log likelihood, and the negative log likelihood has this form. That's the log of the partition function. Okay? And that's the loss function you have to use if you want your system to be probabilistic, to estimate probabilities of y given x. There's a whole bunch of others. Okay, there's like a huge catalog of those things. In fact, I repeated some of the ones that were in the previous slide, but the point here is slightly different, is to figure out to what extent they apply to certain types of energy functions or not. So maximum likelihood, if your y variable is discrete, you can do exhaustive, you can compute the sum if y is the cardinality of y is finite and reasonable. And you can minimize this, no problem. So you can do probabilistic models if y is discrete and small cardinality. If your energy function is such that the integral of the exponential minus the energy function is tractable, then you can just do maximum likelihood again, and you can compute the gradient of this, no problem. Now, if you want to do maximum likelihood, but that integral is not tractable, then you're going to have to resort to sampling, and I'll come back to how you do this. But basically what it comes down to in the end is that you have energy of the data points that you want to push down and energy of the contrastive terms that are sampled from a distribution that you want to push up. And that's whether you use, any kind of sampling method, Monte Carlo, Markov-Chain Monte Carlo, whatever. And then hinge. So if you have hinge and you really want to kind of minimize that term, how are you going to generate those y hats? One possible way is to pick y hat as the most offending incorrect answer. So you search for a bunch of y's. You try to minimize for a given x, you try to find a y hat that has low energy, but yet is wrong. So it's different from y, some distance away, let's say. Okay? And you push that up. So that goes for the jugular, basically, right? It says, my model is going to might be flat, and I'm going to try to find a y that's really close to the manifold of data and push that one up by finding or one that my model gives a very low energy to and push that one up as long as it's incorrect. Okay, so those are called the most offending incorrect answer. So you search, you can have a strategy where you search for this y hat so that you pick a y hat that your model already gives low energy to, and you push that up. And so, it will find areas of the space that your model gives low energy to and systematically push that up as long as those areas are not on the manifold of data. This may be a little complicated to do, but it works. Certainly works for discrete y's. And those are different versions and strategies that you can employ to pick the y hat. But here is something, another class of loss functions that people have been using recently in self-supervised learning particularly, and it's basically a group loss. So it's not a loss that depends on just two samples, it's a loss that depends on a whole bunch of samples. And basically it's a function of one positive sample and a whole bunch of negative samples. Where here this is a general form where you have a whole bunch of positive samples and a whole bunch of negative samples. But really the way people use this is that you have one positive sample which comes from your data set. So it's an XY pair from your data set. And then you take a whole bunch of negative samples with Y's that maybe may come from your data set but are not matched with their X. Okay, so you pick another Y that's not compatible with that X. Or is generated through some process. And you take the list of all those things, plug them into some loss function, and you push and pull. So a good example of that is what's called now InfoNCE, but it's similar to what people are using in the past called neighborhood component analysis or noise contrastive estimation. So that goes back to the mid-2000s from the Toronto group. And the idea here is that you basically do a log softmax kind of thing, where you take the energy of the good guy. There's a minus sign. So this will want to make this energy as low as possible relative to the sum of the energies of the bad guys. Okay, so you normalize by the sum of the exponential of the energies or negative energies for all the samples, positive and negative. Some forms of it actually don't have this term. They just have those. And this will have the effect of making those energies large and that energy small relative to each other. And it also has the advantage of pushing up the energy of the bad guys stronger if those guys are closer to the positive. So if in this sum you have one low energy for one bad guy and a whole bunch of larger energies, the larger energies will not get any gradient from this. Because the value of this would be dominated by the lowest energy term. So this guy is going to get pushed really hard. So that's an implicit way of doing what's called hard negative mining, where the system the function automatically kind of picks the terms, the energy of bad guys that are threatening and pushes them up within a batch of samples.
Maybe if you had to think about doing Monte Carlo sampling, this is global dynamics, meaning if F was given,
sure,
and then you have a Y, and you propose a new one, this is the acceptance. And so you're saying if I propose something which is bad, I should really have a low acceptance, and
right, and there's all kinds of tricks actually to figure out, like, do you build a cache of those negative samples, and so you can reuse the same ones all the time, and you don't have to recompute everything. So there are lots of, but it's true. Okay, GANs. So GANs are secretly a contrastive method for energy-based models, okay? At least if you write them the right way. So imagine you have a loss function that is a increasing function of the energy of data points, and then a decreasing function of the energy of contrastive samples, and maybe with a margin. You don't need necessarily one, but perhaps with a margin. And now imagine that what we are training is some energy model. I put some architecture here that looks like an autoencoder, but it could be anything. It doesn't matter. So you have a neural net here that produces a single scalar output that measures the energy of whatever you feed it. And what you want is you want to, whenever you feed a sample from the training set, you want the energy to be low. And whenever you feed a sample outside of the training set that's generated, you want the energy to be large, right? So that's a contrastive method. But the way GANs do this is that they train a second neural net to generate those contrastive samples. Okay, and they train that neural net, so that neural net takes a random input vector drawn from some power distribution, let's say Gaussian, feed it to some neural net that produces an input of the same nature as the data, let's say an image. And those are supposed to be bad, and so you tweak the parameters of this critic or discriminator so that the energy output goes up. And for data points, you tweak it so it goes down, right? You can use any loss function you want that has this form. So what's interesting about this is that you're going to train the generator to produce points that this guy actually gives low energy to. Okay? So it's a bit like the most offending answer technique I was talking about earlier. Try to find points, y hat, that your model gives low energy to, and push them up, and make sure those points are different from anything in the training set. But there, instead of doing this through some optimization process, you're just going to train a neural net to do that. So you can think of this as some form of what's called amortized inference. But if you don't know what that is, doesn't matter at this point. And so the way you train this generator is that you backpropagate gradient of the energy coming out of this thing to those weights, and you adapt those weights so that whatever is generated are things that this model gives low energy to. Okay? And of course, it's an issue here because you're not minimizing a cost function. You're actually trying to find the fixed point of some adversarial game. So gradient descent may or may not work properly. But it's basically a game. Okay, so now let's connect a lot of that to maximum likelihood methods and show how maximum likelihood methods and probabilistic models are kind of a particular interesting special case of all this. So there is a bunch of formulas that I'm sure many of you are familiar with, but I'm just putting them up here as a reminder. So if you have some energy function of a variable y and you want to turn this into a probability distribution, you use Gibbs formula or something of that type, possibly with a temperature or inverse temperature parameter. You can compute joint distributions by having a normalization term that is the integral over both of those variables. And more generally, anytime you want to turn an energy into some distribution and the energy is a function of multiple variables, whatever is in the denominator are things that you're computing the distribution over, and whatever is not is whatever you condition upon. Okay? Formulas marginalization formulas like this one, P of y given x is the integral over z of P of y and z given x. And of course, it's the integral over z of P of y and z given x, which, we had here. So I just put an integral over z here, and I get sort of the same term, above and below, which I can write as P of y. And you can recover things like Bayes' rule, right? So here's a formula for a joint distribution over y and z, for example, or conditional for y given z. So here I only normalize on y. Here I have to normalize with respect to both. And this is kind of a marginalization formula where I have to, if I want the distribution over z, I have to integrate over y on the top and then integrate over y and z at the bottom. And then you combine all those things and you get Bayes' rule. I mean, it's kind of obvious when you multiply this by that. You get this term at the bottom and at the top. It simplifies and you get that formula, which actually is the same you had upstairs. Okay, so you don't have to remember Bayes' rules if you just work with energy functions. But so to some extent, it's a little more fundamental, actually. Okay, so here's the negative log likelihood loss. The negative log likelihood loss is I'm going to write this down actually on the board. So, and I alluded to this yesterday. So if I want to do maximum likelihood and I have a bunch of training samples, x1, y1, xp, yp, maximum likelihood says I want to find a model, let's say a probabilistic model that is parameterized by a set of parameters w, so that the probability, the conditional probability of all the y's given all the x's is maximized. Okay, find a w that maximizes this. I make the hypothesis that the samples are independent, so I can decompose this product, this joint probability into a product. So basically I want to maximize the product for all I of the probability that my model gives to yi given xi. Okay, that requires this hypothesis of independence of the samples. I don't like to maximize stuff, particularly if they are products, so I'm going to minimize the negative log of that product. Okay, which of course is the sum of the logs, of the negative logs. So I should put this minus sign in front. Okay, so this is the negative log likelihood loss as a function of the parameters and the training sample I'm considering. And actually the training set I'm considering. Okay, because it's an average or sum over. I can, make that more palatable perhaps by dividing by the number of training samples. So I get an average instead of a sum, but it doesn't matter. It doesn't change anything. So now, what is P of y given xi? What is my model P of y given x is a Gibbs distribution. Okay, so I plug this into the log, and what do I get? I get the log of this minus the log of that, right? So I'm going to just insert this into this. So the log is going to cancel the exponential here, and then I'm going to get a log exponential thing with a minus sign in front, but the minus is going to get canceled. So what I get is what's written up there. You get the energy of the good guy, okay, the data point. And then you get this other term. So I divided everything by beta here so that I just get the energy here. But if I don't divide by beta, there would be no 1 over beta here, and there would be a beta in front. But divided by beta, which doesn't make any difference. And this term basically wants to push up on the energy of all of the points, all of the y's, okay? Because it wants to make this entire thing small. So to make this small, you have to make those energies large because they are in a negative exponential. So this is going to push up on the energy of everything, including the good guy. Okay, now I'm going to write this down, then I'm going to derive it, but you're probably familiar with this already for some of you. If I want to compute the gradient, so the gradient of this with respect to W, presumably I can compute because that's some neural net or some parameterized model that computes my energy. I can backpropagate gradient to it, get the gradient of that energy term with respect to the weights. Now, how do I get the gradient of this if I know how to compute the gradient of F with respect to W? And I get this wonderfully simple formula, which is well known by anybody who does Monte Carlo. But the gradient of the log partition function with respect to whatever parameter the energy depends on is going to be equal to the expected value of the gradient of the energy with respect to the parameters, where the expectation is taken over the distribution that my model gives to each of those y's. Okay? And this is super cool because I can approximate this integral by a sum of terms where the terms are sampled from that distribution, and I can sample from that distribution using Monte Carlo method without actually having to explicitly compute the distribution by just working with the energy function. Okay? So that's what it comes down to. That's the loss. That's the gradient of the loss. And what we're going to do is that we're going to sample a sample y hat from that distribution, okay? And then just have one iteration of gradient descent where I'm going to have the gradient of this and then the gradient, and then this where there is only one term in the integral, which is a sample from that distribution. That's going to be my y hat. So that's a contrastive method, okay? I push down on the energy of the good guy. I push up on the energy of the bad guy. It's just that I select the bad guy by sampling from this distribution, which is the distribution that my model gives to each of those samples. And the beauty of it is I don't need to compute the distribution. I can sample from this just on the energy function, which is the basis of Monte Carlo methods. Okay, so what's going to happen is in the space of y, the energy for the correct y, which is right here, is going to get pushed down really hard with a force of 1, if you want. And then all of the other y's are going to get pushed up, but the force with which they're going to get pushed up is proportional to the probability that my model gives to that point. So a point like this one, which has a lower energy than the correct point, is going to be pushed up like crazy with a force larger than 1, essentially. And the other ones are going to get, particularly if they're high up, they're not going to get pushed up very much. Okay, so this is going to have the effect of really pushing up super hard on things that already have low energy. But in the end, the only kind of stable situation is when this guy has as low an energy as possible and everything else has as high an energy as possible. And the bad news is that it's bad. It's bad because this is what happens. So this is kind of the same little architecture I showed you earlier, but then I'm using Monte Carlo sampling basically to push up on bad guys. And what it does, first of all, is that it only cares about differences of energies, doesn't care about absolute values of energy. So it pushes down on the blue points like nuts, and then it pushes up on everything else like nuts. And in the end, what you get is a golf course. If you let the system go for a long time, you don't regularize it in any way, you get a golf course. You get, if your data manifold is thin, you get a very deep trench on the data manifold, and then you get basically infinite energy just outside, epsilon outside of it. And this is a terrible model for inference because you're here and you have no idea where the trench is. You have to basically go more or less exhaustively to find it. It's really bad. So you don't want to use maximum likelihood unless you regularize it. And the way to regularize it is to say, well, I'm going to put a prior on my parameters, for example, so that I don't get this kind of energy profile. For example, I'm going to limit the size of the weights that my model can use. And so the steepness of the slopes cannot be infinite. And my energy function is going to get smooth. So you can certainly regularize this. In fact, that's the whole idea of Bayesian inference. You put a prior on the parameters, and then the prior kind of regularizes your model. But then what's the point of using maximum likelihood if you're going to throw it out the window by putting a prior, which basically is a regularizer with another name?
So I have a question.
Yes.
So in high dimension, all your blue points will anyway be very far away from each other.
Correct.
So how do you avoid all of those methods to create yield between the blue points?
Good point. In fact, I'm going to argue against contrastive method precisely for that reason, that the more the dimension increases, the number of points you're going to have to push up on if you have an infinitely flexible energy function goes exponentially with the dimension, which is why contrastive methods are basically doomed and hopeless. Okay, which is why probabilistic methods, maximum likelihood methods based on Monte Carlo sampling are hopeless. But yes?
But if regularizing is equivalent to a prior, then I can keep thinking about it as a probabilistic method. Why would that?
Well, there are different types of regularization, right? There's a regularization that minimizes the volume that can take low energy, which I talked about for non-contrastive methods. And then there's regularization of the type that prevent, the model from having like super high slope energies, and those are two different types. In fact, the type of regularizer that minimizes the slope actually increases the volume that takes low energy to some extent. So they're kind of different types of regularizer. So let me talk about latent variable models. So a latent variable model, as I mentioned earlier, is one in which you have a latent variable you do not observe. And there's two things you can do with a latent variable model. You can minimize with respect to the latent variable, or you can marginalize with respect to that latent variable, which is the proper Bayesian thing to do. And the minimization is just, you just define the new, the free energy, if you want, as the energy that your system gives to the xy's that you're given, and the z check that minimizes the energy. And then the marginalization, you define the free energy of this type, which is -1/beta log integral of exponential minus the energy, where the integral is taken over all values of the latent variables. Okay, log sum x, which is the stuff that Francis talked about at the end of his, or said he was going to talk about. Tomorrow morning, right? And you can derive this pretty easily. So if I write p of y given x, I have to marginalize over z, right? So I have to integrate over z here on top, and then integrate over y and z, so I get a proper distribution over z. Now, if I define f of xy as the log of this thing, okay, then this formula turns into that one, which is just a Gibbs distribution where the energy now is not the original energy, but is the free energy. Okay, so the advantage of using this formula for free energy is the fact that it still works with Gibbs distribution, and it's a pretty trivial derivation to do. So I'm not going to do it, but that basically gives you a way of defining a proper probabilistic free energy. So let's take a really simple example where, let's say, we have two variables y1, y2, so it's an unconditional model. And our energy function is such that it takes zero value around an ellipse, and then the value of the energy increases as we move away from the ellipse. Okay, so if I do minimization, I give a point y, and I have to figure out what is the value of a latent variable. So a latent variable is going to be something that determines where I am on this ellipse. Okay, so z, imagine that z is some sort of angle. And if I want to minimize my energy with respect to z, what I'm going to have to find is what is the point on the ellipse that is closest to my data point y. So that's the minimization with respect to z of my energy. And my energy is going to be the square distance between the data point and the corresponding point on the ellipse. Okay? So the energy surface corresponding to this little example here is very simple. It's something that is zero here and grows quadratically as I move away from the ellipse, and then goes quadratically as I move away from the ellipse inside, and it's got like a peak in the center. Like that's the peak du midi. And so that would be my energy model with this latent variable. Okay? Il est midi. But we're going to, oh, that's a good point. Du midi, midi, à midi. Le pic du midi à midi. Okay, now if we want to use the marginalization formula, though, the energy of a particular point here is not going to be just the distance with that point. Is going to be the log of the sum of exponential minus the distances. Is going to be minus 1/beta, the log of the integral of e to the minus beta, the distances of that point to every single point around the ellipse. Okay? And so what you're going to have is that the energy of this point is going to be something. The energy of a point that is at the same distance to the ellipse here is going to have a lower energy because there's more contribution from the neighbors. And the energy of a point here, which is at the same distance, is going to have a higher energy because the other guys contribute less because they're farther away, faster. Okay? The analogy of this with things like quantum mechanics is that this is like a path integral. Okay? Think of all of those things as path, and the probability of getting to a particular place is the sum of the probabilities of the contributions of probabilities for all those things, and they contribute to the extent that the probability being exponential minus the energy. So you get contributions to the energy of every point or the free energy of every point from every point around the spiral, the ellipse. Sorry. Okay, things that are of historical importance and which I'll go through relatively quickly. Hopfield nets and Boltzmann machines. So Hopfield nets have a learning algorithm that is non-contrastive, which is why it doesn't work very well, and Boltzmann machines basically are a contrastive version of Hopfield nets. Hopfield net is a neural net with binary activations, the y's, that can be +1 or -1, or 0 and 1 if you want, and then a symmetric weight matrix, and the energy is minus sum over ij of yi, wi, j, yj, so this is like a spin glass, where the spins are +1 or -1. And given that some values of the y's are known, you can try to find the values of the other y's that minimize this energy. And Hopfield made the connection between this and the possible dynamics of neural nets, and that got physicists interested in neural nets back in the early 80s. And in fact, the meeting I was here for in 1985 was populated by people like Hopfield and Scott Kirkpatrick and Daniel Amit and a lot of spin glass physicists who say like, now we can perhaps help understand how the brain works. Now you can easily find a combination of y that minimizes energy by basically saying, I'm going to compute the weighted sum of the yj's through the weights, pass that through a threshold. I'm going to set yi to that. So this is like a binary neuron type rule. And if you do this repeatedly on all the neurons sequentially or in parallel, you will converge to a local minimum of that energy. Okay, and the way you train the system is that you dig holes in the energy surface. So you give a data point y, and then you say for that y I want the energy to be low. So you compute the gradient of that of the loss, which is just the energy of the point. Okay, it's the energy loss. And you just dig a hole at that place, so compute the gradient of the loss with respect to wij, you get minus wi, wj, and then you just update the weights. Wij is equal to wij minus the gradient with some step size, but that's immaterial, plus ya, yj. This is what neuroscientists call Hebbian learning. So whenever two neurons are active simultaneously, increase the weights that connects them. Okay, and that will dig a hole at that place in the energy surface. The problem is there is no contrastive term, so there's no guarantee that there's not going to be other places in the energy landscape whose energy is also going to be bad, and people at the time called this spurious minima or spurious memories. And so this actually totally sucks if you want to use it for anything practical, like associative memories. But conceptually it's very interesting. So Boltzmann machines, which came out the year afterwards, and Sinovsky was actually a student of Hopfield and actually got Hopfield interested in this, to me was a complete watershed, because this was the first paper that talked about hidden units, and so basically neurons that were not observed, neither inputs nor outputs. Here I wrote a version that only has outputs, but you can imagine having inputs, so it would be another x variable that is essentially constant, determined by the outside, but the formulas are the same. So you have weights that connect the y's between them, which is like Hopfield. You have weights that connect the z's between them, and you have weights that connect the y's and the z's, and then you have this idea of restricted Boltzmann machines, and in a restricted Boltzmann machine you only have this term, you don't have the other two. Okay? And so you can define a free energy with respect to y by marginalizing over z, if you want, and then apply a contrastive learning using the negative log likelihood loss. So this is negative log likelihood loss, where you have the energy of the data point plus the log of the sum of the exponentials of the energies of all the points. Okay, so this is going to, and there's a minus sign here. So this is going to push down on the energy of everything, and this is going to push up on the energy of the data points. Now you cannot compute this because the number of different y's may be combinatorially large. So you're going to have to basically approximate this by sampling. And the problem is that you have to sample not just the y's, but also the z's. So how do we marginalize on the z's? So basically we're going to do Markov-Chain Monte Carlo sampling on the z's for the first term and simultaneously on z and y for the second term. So the first term really is a free energy with respect to y, and I can compute the gradient of it in this form. So this is the sum over both y and z. I'm sorry, this is the sum over z. There is no y here. That's a mistake. Of the probability that my model gives to this particular z for the observed y multiplied by the gradient of the energy with respect to the weights at that location. And the way I'm going to estimate this is I'm just going to sample from that distribution. So I'm going to keep the y fixed to whatever I'm given from the outside, and then sample z according to that distribution. I'll tell you in a minute how. And that's going to give me, and then compute the gradient at that location, and that's going to give me that first term. And then the second term, I'm going to have to sample simultaneously from y and z from that joint distribution, and then compute the gradient at that point. And that's, in the end, that's going to be super simple, right? Because the sample I get from here, which is a sample from this distribution, okay, which I can do with Monte Carlo, Markov-Chain Monte Carlo on the basis of this energy. I'm going to plug into the first term. So this is the gradient of the first term, because the energy is just a quadratic form. When I differentiate with respect to wij, I'm just going to get yi zj check, which is the sample I got from this. And then the second term is a sample I got from this joint distribution, which I'm going to call y hat z hat. When I compute the gradient of that, I'm going to get that, right? So I get a super simple learning procedure in the end, where I take the weight wij and I update it with some constant times the difference between the, there should be a check here, the product of yi z check j minus y hat, yi hat, and zj hat. Okay, so this is called the positive phase, and this is called the negative phase, and this basically generates contrastive samples of y's. This generates, this marginalizes over z, and this also marginalizes over z. That's the Boltzmann machine learning algorithm. Now, how do we get samples from those distributions? It's very much the same as the Hopfield net. And I'm only talking about getting samples for z, but you have a similar formula for getting a sample from y. Basically, what you can do, so that's the form of the energy function. And what you can do is compute the difference between the value of the energy for zi equal 1 and the value of the energy for zi equals 0. And just like in a Fermi-Dirac thing where you have two levels of energies and you're trying to figure out what's the probability of being in the high energy, you plug this into a Fermi-Dirac distribution, and that gives you the probability of being in the z equal 1 state in such a way that it preserves the detail balance. So, and in fact, the difference between those two energies is just the sum over j of wij, yj. Okay? So to compute a z, you take the weighted sum of the y's with the weights that connect to that z, then you pass that weighted sum through a sigmoid function, and then you use the value of that sigmoid as a probability with which to set z to 1. Okay? And you can have a gain in it with the temperature or whatever. Okay. This was kind of fashionable for a bit and then quickly disappeared because basically those sampling stuff, it takes a huge amount of time and are very inefficient, and it's a contrastive method that if y is a high dimensional space, there's like so many possibilities that the sampling is going to take forever. So nobody actually ever used this for anything practical, but it's conceptually really interesting, and it's just an example of contrastive method. with MCMC approximation of the log partition function. Denoising autoencoders and masked autoencoders. So this is a practically very relevant set of techniques, and you can interpret them also in terms of energy-based models. So what is a denoising autoencoder? It's basically an autoencoder. So you have, it's an autoencoder, but what you train the autoencoder to do is to restore a clean version of a corrupted input. So you take an input, you corrupt it in some ways, which means you move outside of the manifold of data. Okay, you get a data point that's on the manifold of data. Why? You corrupt it, and then what you do is you train this neural net to recover the uncorrupted version. Okay? So what is that going to do? Okay, so here's the example. So we have data points along the spiral, and those brown points here are corrupted versions. So each of those brown points is actually a corrupted version of a blue point. And so we take a brown point, and we're telling the system the energy of that point should be the distance of the brown point, the corrupted point, to the original point. Because what I'm going to do here, by corrupting this thing and training this guy to reconstruct the original point, what that means is that when I now take a corrupted point that I plug here, or that I plug here, when I run it through the autoencoder, it's going to produce the clean point, and so the reconstruction energy is going to be the distance between the bad point and the good one. Okay, I'm training the system to basically say, so let's imagine this is a squared error. Okay, I'm training the system to give an energy to every point that is equal to the square distance of a corrupted point to its clean version. In particular, if the corruption doesn't do anything, okay, I'm training, so I can corrupt with several levels of noise, one of which could be 0. So if I do not corrupt y, I'm going to train this autoencoder to just reconstruct y. Okay, so reconstruction error, which is the energy, is going to be 0 on the data manifold, and is going to grow quadratically as I move away from the data manifold.
So if the corruption would be, for example, occluding part of the image, that would be what you call self-supervised.
That's right.
So that includes.
So this is what's called a masked autoencoder, where you take a piece of text, for example, and you mask some of the words, and then you train this system to recover the missing words. It's a particular type of denoising autoencoder, and it's called masked autoencoder because the corruption you apply is masking. Now, this is unbelievably successful in terms of practical applications, like insanely successful. Not for like little things like this, but for this type of training, to train text understanding system, translation systems, anything that has to do with text, like language models, whatever. Less for images. Although there's recent work that changed this. So here is the energy surface you get by training with this particular data set. You actually get something really weird, which is not exactly what you want. You get 0 energy on the data points, okay? This vector field here is the gradient vector field of the energy, okay? So the color indicates the energy level. So you get high energy outside the manifold of data. You get high energy as you move away from the manifold. But you get this weird thing here right in the center where the energy is kind of 0. Because when you train on the point here, half of the time it's going to be attracted to a point here and half the time to a point there. And therefore, those points are going to get stable, okay? And so if you have folded manifolds, the sort of denoising autoencoder idea is actually not a very good one. But now in high dimension, it's okay. You're not going to have kind of folding manifolds like that. So hopefully.
So why is not the maximum?
Say again.
Why is not the maximum?
Why is not a maximum? It's because when you train the system, you're going to take this point, and then occasionally the noisy version, the corrupted version, is going to be here, and then for this guy, is going to be here as well. And the number of times you're going to get a clean sample coming from the left or from the right is going to be equal. And so this guy is going to be trained half the time to go here and half the time to go there. And so it's just going to stay here.
No, but the energy is the distance, right? It's always going to be far
is trained to be the distance, but it's not the distance in the end. Okay. Now, there is a slight modification of this, where you put a latent variable and you minimize over that latent variable, and it completely solves that problem, but I don't want to go into this. So examples of insanely successful uses of masked autoencoder is for language models in particular. So you pre-train. So this is a open source model that was produced by some of my colleagues at FAIR, and a large collection of colleagues actually. And it has 175 billion parameters. There's actually several versions of different sizes. And you pre-train that system to basically fill in the blanks in text. And you test it on sort of various downstream tasks where you train with whatever data you have available. And the pre-training really improves the performance quite a bit for all kinds of tasks, including things like hate speech detection and a collection of NLP benchmarks that are fairly popular, different ratings of dialogue systems, etc. This requires a pretty big infrastructure to train, but you can run it on pretty much anything. So you can use those systems in certain forms of it to generate text, because a form of it, you just mask the last word, so you can get the system to just generate text. So you initialize the system by just typing a prompt, what's called a prompt. This is an initial text that you feed to the input of the system, and then you let it predict the next word. It produces a distribution over words. You sample from that distribution, some giant softmax. So you take a sample from that distribution, which happens to be understand. You feed that back into the input, and then have it generate the next word, and then it's going to keep generating words. And it's grammatically correct. Spelling is correct. Everything looks fine. If you have it generate for too long, it becomes kind of a little incoherent. But so there is kind of local coherence, but not really long term. So there is a fun dialogue. The prompt is, this is a chat between the curious humans and the Statue of Liberty. Human, what is your name? Statue and the Statue of Liberty. Human, where do you live? Statue in New York. Human, how long do you have lived there? And then you let the system complete, right? So the rest is produced by the system. Statue, I have been there since 1886. Human, what is your job? Statue, I was built to welcome immigrants to the United States. Human, what is your favorite food? Statue, I like ice cream and apples, right? Obviously, the system doesn't know that statues don't eat, but it has no notion of underlying reality. What is your favorite color? Red, white, and blue. That's kind of a nice answer, etc. Here's another example. So this was released just last week or 2 weeks ago, again by some of my colleagues at FAIR. It's a project called No Language Left Behind, NLB, and this is a system that can translate from, that knows 202 languages and can translate from any of those languages to any other. So that's 40,602 directions. It was trained on 18 billion pairs of sentences, so this is supervised learning. But it was pre-trained using self-supervised learning, basically by being trained to complete missing words in sentences in sort of monolingual text. So you can use text in a language to learn the structure of the language without having parallel text to translate into another language. So the system knows the structure of that language by just having been pre-trained on those texts. And then you train the translation system, and you don't need to train it with a lot of data because it's already figured out the structure of the language. And what's more is that the number of pairs of languages that those 18 billion pairs of sentences come from is only 2,440. So you don't need all examples for all 40,602 pairs of languages. You just have examples for a few pairs. In fact, most language pairs have less than 1 million sentences, so which is kind of relatively small. And this is open source and everything. There's a very long paper that describes the whole thing, and the magic of it is that this actually works better on any individual language than a previous system that was only trained with 100 languages. Okay, so the more language you learn, the easier it becomes to learn new ones. It's true for humans too. But humans are limited to 5 or 6 or something. Now, 200 languages, you think that's not that much, given that people in the world speak 6,000 languages or something like that. But in fact, here's a list of languages, and many of them, I have no idea where they come from. Like, do you know what Jingpo is? No idea. Kamba? Canada, I know because I've been there. But it's not Canada, it's actually southern India. Marathi? Minangkabau? Quechua, that's a Native American language. Yeah, so some languages appear twice because there's two different writings for them. So, Armenian?
It's in the third column.
Where is Armenian? Well, it's not a complete like alphabetical order. I'm not exactly sure what order they've used. Right.
Yeah, it's not alphabetical.
So they do have. So they have local dialects like Occitan. So Occitan is spoken in southern France, southwestern France. Not spoken very much, but spoken.
So it's only live languages? There is no Latin or Sanskrit? Or...
No, they don't have those, but they could. Like in some experiments, they actually did like Klingon. You know, there's apparently enough text in Klingon that you can actually make those things work.
Negative, but I don't see Corsican.
There is no Corsican. There is no Breton. Yes, what's going on? Okay, so this works really well for text. It doesn't really work for images. So people, of course, have tried to do those denoising autoencoders. This work by Patak, for example, going back 5 years, where you take an image, you corrupt it by sort of blanking out some areas, run this to an autoencoder to recover the original image. And the features you get out of this are not very good. Like you plug them as, so you take the representation learned by the system and plug them as input to a classifier that you test on ImageNet, and you get like 40% correct or something. It's really not that good.
Is it good at the task that it's trying to do?
I mean, the task is not a task. It's a surrogate task, right? The completion. Yeah, it's pretty good at actually recovering. In fact, that's an example of reconstruction. And the problem is that probably the reason why it is this way is that, again, it's a multimodal prediction problem. There are many different ways to fill in this area that are all plausible, and you're training the system to just produce one. I put a latent variable here, but there's in fact no latent variable in this model. So the system basically makes some blurry prediction. It's the same problem that we saw with video prediction. It's just a multimodal prediction problem, and those autoencoders are very bad at it. Now, I should say that there's a very recent work, again by some of my colleagues at FAIR, Kaming He in particular, where they used what's called a masked autoencoder for images, and they managed to make it work, but the only way they could make it work is by using a transformer architecture here, and basically by masking what's called tokens at the input of that thing. It doesn't work with a convolutional net, for example, at least not yet. Okay, I have about 5 minutes left, because we started 15 minutes later. Yeah, I looked at it. I have my phone right here. I'm not going to use 5 minutes. So it's just a preview for what I talk about tomorrow. And this is really about proper architectures. So this is a generative architecture where, as I said before, plug an X, make a prediction for Y, and then compute the divergence between X and Y. If you want this to be multimodal, you have to have a latent variable here. Okay? Otherwise, you're not going to get multimodal prediction, and we're not going to be able to use this for training a system to do video prediction or whatever, or completing blanked areas in an image. And this is a joint embedding architecture, so the difference is here, Y goes into an encoder, and you get an abstract representation of both X and Y, Sx and Sy. And and you do the prediction in that abstract space. So the energy is the prediction error of Sy given Sx. And the advantage of this one is that it cannot collapse, because it's basically regression. The disadvantage of this one is that it can collapse. And the question is, how do we prevent it from collapsing? We can use contrastive methods, but contrastive methods are not that good because, as we mentioned just previously, if the dimension of that space is high, then the number of contrastive samples you're going to have to come up with is going to have to grow exponentially with the dimension for a highly flexible energy model. And so that's kind of hopeless. So I'm going to talk about non-contrastive methods for joint embedding architectures, or in particular for joint embedding predictive architectures. And this actually works. And those techniques have appeared in the last year or two, and I think are the best thing since sliced bread. I haven't been excited about anything like this since convolutional nets, so that tells you something. But we'll talk about this tomorrow.